Okay, so now that we have defined what a principal component is, I want to use that to define principal component analysis, which can be seen as a way of approximating the data in a low dimensional space. And this is a pretty mathematical section, so we're going to walk through some of the details of quantifying exactly how good that approximation is, so you'll get a geometric mathematical understanding of when PCA works well. So principal component analysis is really about finding low dimensional representations of data. So let me try to mathematically make that concept precise. So we have some data records xi, and each record has p features. So it's sitting in some p-dimensional space, which is potentially very large and too difficult to work in. So what we want to do is try to find some lower dimensional approximation of that. And by this, what we mean is that we're going to take each data record and approximate it by the mean plus some linear expansion in some basis. And we'll use just d terms in this basis. So if we think about it like geometrically, we have our data record and there's some smaller d-dimensional space that I'm trying to represent each vector xi in, and that representation is called x hat I. Now, the dimensionality reduction comes from the fact that if this d is much smaller than the original dimension p, we're effectively representing that vector by a smaller number of coordinates, because we can just represent that vector by the coordinates in this d-dimensional basis, or this d-dimensional space here. So as long as this approximation is good, that is, we can find a subspace where all the data records are close to that subspace, we're not losing much information, but we're being able to represent it in a smaller number of coefficients. And that is the basis for what we mean by a low dimensional representation. Now, one thing that we're going to do throughout this is just assume that we're going to work on what are called orthonormal sets and bases, which will make the computations simpler. So if you have seen, let's say, signals and systems, you would have seen this, but if not, no worries. I'm just going to review it here. It's a pretty simple concept from linear algebra. So if you have d vectors, say potential basis functions in this lower dimensional space, they're called an orthonormal set if each vector has unit norm. That is where the normal part of orthonormal comes from. And if I take any two different vectors, they are orthogonal. So that means if I take their inner product, it is 0. So that's the mathematic or algebraic definition. But in just regular geometry, say in three-dimensional space, if I took these three red vectors, they would be orthonormal if their length is 1 and they're all at 90 degrees with respect to one another. It's often convenient to write these conditions in matrix form. So we define a P by D matrix with the columns of these D vectors. And then you can easily check that these conditions are the same as V transpose V is the identity matrix. The reason is that the diagonal elements of this matrix will just be these inner products, and they must be 1. And the off-diagonal elements are these inner products, which must be 0. Now, in the special case where D is equal to P, that set of vectors is called an orthonormal basis, and this matrix V will be P by P, and it will be called an orthonormal matrix. Key property for our purposes is that the principal components always form an orthonormal basis. And that just is a linear algebra property that they're coming from eigenvectors of a positive symmetric matrix. I'm not going to prove that, but let's just take that to be true. Now, whenever you have an orthonormal set or an orthonormal basis, one very nice thing about it is that you can compute the coefficients of any vector in that orthonormal basis very easily. So to make that clear, let's say that V1 to Vp is an orthonormal basis, and I'll walk you through some calculations to make sure you understand. And now I give you any other vector in Rp. Turns out that that vector can be written as a linear combination of the vectors in this basis, and these coefficients alpha j can just be found by the inner product of the basis vectors with z. So it's super easy to compute these coefficients. We can write these coefficients in matrix form by just saying that that vector of coefficients is just V transpose times Z, because every coefficient in alpha j will just be this, and similarly that Z will equal V times alpha. Now let's take a look at how we can apply this concept of orthonormal bases to our data matrix. So again, we have n data records which are sitting in some p-dimensional space. And let's say that we compute the p principal components. Again, the p principal components are just the eigenvectors of the sample covariance matrix. Now what I can do is I can say that every data record xi is just the mean of the data set plus the plus the coefficient or linear expansion in the basis of these principal components. So each coefficient, you'll have p for each data record I, you will have p coefficients alpha ij, which can be found by the inner product of the jth principal component with the difference of the data record from the mean. It's basically the identical formula to what we had before, excepting we've subtracted the mean here and then added it back at the end. Now, what's useful about this is I can say that instead of taking this xi, I can take an approximation of this by this expression here, which is identical to this, excepting I'm just taking the first d terms. And the key concept here is that if I use just d terms, I can represent each vector I at least approximately by just d coefficients. So if these d coefficients are much smaller than p, I've effectively reduced the dimension of the data. Let me show you what that is geometrically. So if you have any vector x, what you're doing in principal component analysis is that we first subtract off the mean, and then we look at the space spanned by some smaller set of d of these principal components. And in this picture, that's shown by this yellow plane here. And then the approximation is found by projecting that x minus x bar onto that plane. And then we can get back our x hat by adding back the mean. So it's just really subtracting off the mean and then projecting onto this d-dimensional space. And then after this, we've now done the dimensionality reduction because all our approximations are living on this lower dimensional space. Let me just show you one more illustration of this, which I took from the web. So let's imagine that we have 3 dimensions, 1, 2, and 3, and our data is sitting in this 3-dimensional space. But really, most of the data is very close to this plane, which is shown here. So what we do in principal component analysis is we kind of subtract off the mean of this plane and then project all the data records onto this lower dimensional 2-dimensional space here. So those blue points get mapped onto here, the green points mapped to here, and so on. Now, if this, say, were a classification problem, since we're not losing, hopefully, much information, we could still, for example, classify the data well, even just using these 2 principal components as opposed to 3. Now, in this particular case, you're not getting that much data reduction because you're just going from 3 to 2. But in reality, in most cases, you might be going down from, say, thousands of features to maybe tens of features. Now, let's just do a quick calculation to make sure that you understand the concepts. First, let's say I give you 2 vectors in R3, like this, and I just ask you to show that they are orthogonal. That's super easy to do. All you have to do is verify the conditions that I said. So you want to show that V1 transpose V1 is 1. And that's easy because I just go, if I take the inner product of this, it's 1 squared plus 1 squared plus 0 plus 1/2, and that will equal 1. And similarly for V2, you'll get a 1/6 plus a 1 squared plus minus 1 squared plus 2 squared, and that you can check is 1. And if you take the inner product of the V1 with V2, you'll get 1 times 1 plus 1 times minus 1 plus 0 times 2 plus these scaling factors. And when you add all that up, you will get indeed 0. So this is an orthonormal basis. Now, let's say I have these two vectors, or the 2 principal components, and this vector was the mean of the data, and I wanted to find the approximation of some data record like 244. Now this, I'm just taking made up these numbers just to make the calculation simple. It's not really representative of any real data. So what do? The first thing you do is you take your data record and you subtract the mean. So you're going to get 2 minus 0, and 4 minus 1, and 4 minus 2, 2, 3, 2. Then you find the coefficients of that de-meaned data with respect to each of the principal components, and that's found from these inner products. So I take the inner product of V1 with this difference, and you get 5 over root 2. And then you take, for the coefficient of PC2, you take that inner product with V2, and you can work that out, and you get 3 over root 6. Then, finally, the approximation with respect to these 2 vectors here is you add back the mean. This adding back the mean is important. And then you just add the linear expansion with respect to each of these PC component vectors. And you go through this. It's kind of time consuming if you're doing it by hand. We'll show you how to do everything by computer momentarily. When you add all these numbers up, you get 3, 3, 3. So it's not exactly equal to this in this case, but you see it kind of approximating it. Hopefully in reality, when you take the 2-term approximation, you wouldn't lose as much of the information. All right, now that we know the mathematics of computing the principal components, let me try to show you what the average approximation error is, so you'll get an idea of when principal component analysis will work and when it won't. Okay, so let's let x hat I be an approximation with just d principal components. So I'm not actually explicitly showing the d in this value, in this approximation here. Now, the error on the sample I, you can easily verify, is just the error from ignoring the last p minus d coefficients. So that is where this comes from, this sum here. And you can show, and maybe I will leave this as a homework exercise for you, that if you looked over the whole data set and then you looked at the average error, you will get a sum of the eigenvalues of that covariance matrix, those last p minus d eigenvalues. So I'll give you an example momentarily. So one way to think about this is what is called the proportion of variance. Now, the variance of the total data set, which is the average difference between xi and the mean, you can work out. It turns out to be the sum of all the eigenvalues. And I'm not going to prove this, but it's not that hard to show. You just work it out with a sample covariance matrix and some simple linear algebra properties. And we saw that the average approximation error was just the value of the sum of the smallest p minus d eigenvalues. And so we could say that the proportion of variance is the difference between these, which is the sum of the first d eigenvalues divided by the sum of all the d eigenvalues. Okay, that was a lot of formulas, so let me just walk you through a simple example. Suppose I had a data set, say, in 4 dimensions. Typically you have much more, but I'm just going to make this simple. And the eigenvalues were like this after you sort them. So if you used just one principal component, the amount of variance that that principal component would capture would just be the variance in that first dimension divided by the total variance, which is just the sum of these eigenvalues, 10 plus 4 plus 0.2 plus 0.1, or 14.3. And when I divide that, I get about 70%. So actually in this particular case, because you see that a lot of the energy is concentrated in that first space, you're actually already capturing 70% of the data or the variance just using one principal component. In this particular case, if you use 2, you'd be actually capturing 14 out of 14.3 because these two eigenvalues are very small. So you'd actually be capturing 98% of the variance. And if you go ahead and add that third one, you'd be getting 99. And once you add all 4, you'd be getting 100% of the variance. So this simple example shows you from an eigenvalue perspective when PCA will work, and that is when typically you have a large number, a few very large eigenvalues indicating that the data is mostly concentrated in a low dimensional space. And then you can use that to approximate the data well in that low dimensional space. All right, a couple more things I want to wrap up in our discussion here. And one is the concept of latent representations. So remember that each data record xi is really just, I'm writing as the mean, or approximately as the mean, plus some linear expansion in these principal components. So what then we can think about this is what you would say that each coefficient represents some what you call latent components. So that this might be a high dimensional object, but the variation across the data is explained by a relatively small number of underlying factors. So just as an example, which we will return to if we get to talk about recommender systems, is the following. Suppose xi was a vector of a list of movie preferences for some customer I. So let's say that there's a large number of movies, and this might be xi would be the ratings of that customer across this large set of movies. Now, obviously, movie preferences are highly correlated. If you like, say, one Western movie, you might like another very similar Western movie. And therefore, you could imagine that the movie preferences are actually explained by a small number of latent components, like whether the movie is an action movie, a romance, or maybe the presence of famous stars like Brad Pitt or something like this. But there's a relatively small number of underlying variables that explain all the variation or most of the variation across the data set. And PCA is in some sense trying to uncover these latent representations of data. Let me just show you one visualization of this, in a particular sociological example which comes from the text. In this case, there are a number of US cities, and in this for each city there's 4 types of crime that are recorded: rape, assault, murder, and some property crime. And of course these would be likely to be correlated. You imagine that in cities where there's a high level of assault, for example, you might have other types of violent crime. And so what this 4-dimensional representation could then be represented in 2 dimensions. Now, you can do 2 things once you have that PCA in that 4-dimensional space. The first is that you could go back and plot each city in this 2-dimensional space, and you could see which cities are similar. So it's good for visualization, or which states actually, not which cities, sorry. So for example, New York is close to Arizona and close to Illinois, but very different than, say, West Virginia. At the same time, you can also see the representation of the underlying features in this space. And we can see that here by the rape or the assault or murder and so on. And this is called the biplot, which lets you understand those features in that space. So that wraps up some of the approximation mathematics. I know there was a lot of math and calculations and formulas. So before going ahead, I want you to go to the in-class exercise on the GitHub site and just make sure you can do these calculations. It's really hard to learn these unless you've actually had to compute them yourself. There's so many little details. So we'll go back to that very simple 2-dimensional data set and make sure that you can compute the approximations, the approximation error, and get them to match up with the eigenvalues. And once you've done that, go ahead to the next section.